It's so sad. It's so sad.
Okay. All right. So chapter 8, as you've probably seen, is mostly concerning drawing Lewis structures, right? It's, covalently bonded molecules. And so we talked about the octet rule, right? Which we'll talk a little bit about today. So that's the rule, the idea that 8 valence electrons seems to bring stability to many substances. And those 8 electrons can either be in the form of lone pairs, so they're controlled completely by the atoms. So for example, oxygen can have lone pairs. And each lone pair counts as 2 electrons. Or it can be a pair that's shared with other atoms. So for example, this oxygen may share a pair of electrons with a hydrogen, and maybe with a carbon. So the total number of electrons, of valence electrons, that the oxygen atom has is 8. So let's take a look at an example here. In this problem, it says we're going to draw a Lewis structure for the formaldehyde molecule, which is CH2O. And we want to make sure we draw all the resonance structures that satisfy the octet. So CH2O. Now, when you have organic compounds, it's a good idea to think of the carbon as the central atom. Okay? So in CH2O, all the atoms that come after the carbon are attached to the carbon. Okay, so CH2O would be written like that. So each hydrogen is attached to the carbon and the oxygen is attached to the carbon.
I want to put the 2 hydrogens what? The order of the hydrogen and the oxygen, you could change it?
Yeah, you could put the oxygen up here, or you could put the oxygen over here. It doesn't matter where you put them. You could also do it like this. You could say, look, I just want to do it over on the other side. I want to put the oxygen over here, and a hydrogen here, and a hydrogen here. That'd be okay too.
If it's safe for the hydrogen, like the oxygen between the 2 hydrogens, wouldn't that be another?
Right. So if we're going to have an OH, it will typically look something like this. You'll see it written as an OH. And that tells you right there that the oxygen is attached to the carbon. And then that's okay. Nice. That's okay. Usually these days they're okay as long as they're close.
This is a bar from a king bar.
I'm sure they're okay. The big technique. So if you see OH, then it's going to be COH. But if you see CH2O and there's no H after the O, okay, then the H's here are going to be around the carbon. In fact, even here, right? These hydrogens are going to be around the carbon. So it would be like this, CH3. There's certain things that you can't have this, for example. You can't have CH and then like no. You can't have a hydrogen in between 2 atoms because the hydrogen atom is stable with only 2 electrons. So it can never have more than 2. So that means it really can't be in the middle. There's, usually there's, I would say, a few kind of common structures. So anytime you say, so for example, if you say CH, or CH2, or CH3, those hydrogens are going to be attached to the carbon. So this would be, CH. CH2, CH3. So it may say, for example, CH2O, but you're still going to follow, oh yeah, CH2, but where else can the oxygen go? It's got to go on the carbon, right? It can't go to the hydrogen. So it's got to go on the carbon. So CH2 has this skeleton. Just write the oxygen. That's called chronology. And once you've got the skeleton, then you just start doing the kind of what I call bookkeeping. You're counting electrons and everything. So carbon is in group 4A. Hydrogen is in group 1A. And oxygen is in group 6A, right? So that tells you how many electrons, how many valence electrons they have. The carbon has 4 valence electrons. Hydrogen has 1 valence electron. Oxygen has 6 valence electrons. But there are 2 hydrogens. So we have to say, hey, look, there's 2 there. And if you add these together, it looks like it's 12, right? That would be 12 valence electrons. Once you've got 12 valence electrons, then what you do is you say, well, how many have we already put into the Lewis structure? We put a bond here, here, and here, so that's a total of 2, 4, 6. So we've already used 6 of the 12. So we subtract those 6. And that means we have 6 left. Now, what I typically advise people to do is to take the remaining electrons and write them as pairs on the surrounding atom until you run out of electrons. Now, I stopped by putting 3 pairs, 2, 4, 6, right? Each of the lone pairs is 2 electrons. So that's 6, so we've used them all. Okay? Now, if I had 8, then I would do 2, 4, 6, but we wouldn't want to put another pair here because that would give us more than 8. So if you still had a couple of extra electrons, you put them on the next atom. So try to avoid getting any of the atoms more than 8 electrons. Stop at 8. And what will happen is, you'll find that there's some position for it.
How would I know to put on the oxygen going forward or extra?
So you don't have to, but that's my advice. My advice would be to put them on the outermost atoms first. Okay? So if you have, for example, sometimes this occurs. You might get something like this. And let's say I have 10 electrons, 10 valence electrons. Then same idea. This is on the outside, this is on the outside, so do these. 6 there, and 4 there. Do the outside first.
Wait, why not hydrogen?
Because hydrogen can only handle 2 electrons, 2 max. And it already has 2. Yeah, so that's it. So you will never see Lewis structures, like this. You'll never see that, because that would be 4 electrons.
So the bond is always.
Yeah, bond is 2 electrons, exactly. So really what we're doing is we're saying, look, there's got to be a bond between these atoms, so we're putting 2 at the beginning. Now there might end up being more than 2, there might be 4, there might be a double bond, but there's got to be at least 1 bond between 2 atoms that are bonded to each other. So that's why we have 2, 4, 6, and then we need another 2, 4, 6 to give us a total of 12. So the carbon should end up having 8. We want to have 8 around every atom except hydrogen. But this carbon only has 6. That's why you put a double bond, exactly, to get the carbon up to 8. Essentially what happens is atoms will form the number of bonds it takes to get up to 8. That's what they do. So if an atom only has 6, it's going to draw a couple electrons from another atom to get up to 8. So here's how you do it. You say, look, the oxygen already has 8, so if I push a pair in between, now that pair is going to be shared by both electrons. It's called electron pushing. And so you say, look, there's going to be a new Lewis structure, so you use this double arrow. The new one is going to have this pair as a bond. So you'll have this part of it's not going to change at all, but now we're going to have a double bond. Okay, so that pair there has now become a second bond. And now the carbon has a total of 8 electrons. Before it only had 6, but now it has 8. The oxygen did have 8, but it still has 8. By sharing 2 pairs, these 2 atoms both have 8 electrons. And that appears to be a very powerful driving force in nature, is that these non-metals share the same number of electrons that it takes to get up to 8.
I'm confused. How do you get how do you know the carbon?
How do I know carbon what?
Before 8.
How do I know it's got 8?
No, when you do the C4 8, like.
Oh, these are the family numbers in the periodic table. So you pull out a periodic table, and then the family number is going to tell you the number of valence electrons. Yeah, that's the easy part. Just look it up in the table. Now, in this question, they say, draw all possible resonance structures that satisfy the octet. So what they're saying is there any other way we could do this Lewis structure that's different, but still the carbon has 8 and the oxygen has 8? And looking at it, I don't see any way you could do that. What we could do in theory is take another pair, make another bond. But what that would do is it would give the carbon 10 electrons. So that doesn't seem to work. We can't do any like double bonds to hydrogen because hydrogen has the dual rule. So it looks like we're stuck. It looks like there's really nothing we can do to make a different structure that satisfies the octet.
Is it counted differently for oxygen and hydrogen switch places?
So the idea here is we're just going to move electrons around. You can move atoms around. But really what we're doing is we're saying, look, given this arrangement of atoms, what's the arrangement of electrons? We're looking at the arrangement of electrons.
So when we count the different structure.
Right, so if I did this, if I did, for example, this, that looks different, right? But it's actually not different. It's the same because there's a central atom, which is carbon, central atom, which is carbon, one surrounding oxygen, one surrounding oxygen, 2 surrounding hydrogens, 2 surrounding hydrogens. So the attachments are actually the same here as they are here. It's just arbitrary which way you present it.
Hydrogens on that side, the original, because here the hydrogens are next to each other, and there the hydrogens will be around the oxygen.
But keep in mind, think of it like a tree. This is the central atom. This is the central atom, right? So in both cases, the central atom is the same. And in both cases, you have the same 3 surrounding atoms. These are all the same, right? 2 hydrogens and 1 oxygen. So that would be the same structure. It's just oriented differently.
It was just one thing. If that hydrogen would be there.
So this hydrogen were where? Like over here?
No, the one of that. This one, the atoms.
Like over here?
Yeah, that's different.
It's not really different, right? So if I did that, if I put in terms of its structure, there's a central carbon atom, that's at the center. So how would you define, the arrangement?
Because it's not just just rotated. That one's the same as this, just rotated. This one's actually different.
Well, is it in its essence, is it different? Like in each case, there's a carbon in the center, which is sort of the root. And then there are two hydrogens attached to the carbon, two hydrogens attached to the carbon, and then one oxygen attached to the carbon, one oxygen attached to the carbon. So in its essence, it's the same thing, right? Right? Like I could do this, I could say, look, I'll bend it like that, right? It looks different to your eye, but in its essence, like, think about it this way, like, I can bend my arm into different directions, but this arm is attached to my trunk, right? To the shoulder. So it's the attachments is really what we're looking at, which is this. Now that comes into play. What you're getting to is actually the shape. And the shape is actually an issue, and we'll get to that in chapter 9. But for right now, we're just looking at the attachments and then the positions of the electrons. Okay, so for that one, it looks like there's just one Lewis structure. So let's see if we'll look at a different. Okay, SO3. So this is sulfur trioxide. We're going to draw the Lewis structure for this one. And it says to make sure you include all resonance structures that satisfy the octet rule. So let's begin with the attachments. So we have one sulfur and three oxygens. So we put the sulfur in the center, and then we attach three oxygens. And usually what I recommend is when you do these attachments, think of like a little box, just like we did with the Lewis dot symbols, you know, top, bottom, left, right. And it doesn't matter which one you pick, but just pick three of them. Okay? You know, technically it's not incorrect to do this. You could do this. That would be okay too. But in general, the advice that we give to people is, at least at the beginning, kind of do it like a box, and then go from there. Okay. So now let's count up valence electrons. Sulfur is right underneath oxygen. So oxygen is in group 6A. And so is sulfur. Actually, sulfur in some ways has some similarities to oxygen because it's in the same family. Selenium is right underneath it. So that means each oxygen has 6 valence electrons, and each sulfur also has 6 valence electrons. How many oxygens do we have? 3. So 6 times 3 is 18. And then we have 1 sulfur, so that's 6. So we have a total of 24. 24 valence electrons. Now, we've already used 6. 2, 4, 6. So we subtract those. These are the ones that are already used. And that gives us 18. That's the number remaining. And then again, what I would suggest, it's kind of a standard method, you put lone pairs on the surrounding atoms first, get them up to 8, and then stop once they're up to 8. If you have any extra, then you put them on the central atom. So if I had 20 electrons, I would end up with a pair over here on sulfur. So let's do 2, 4, 6. Now the oxygen has 8. 2, 4, 6. Now the oxygen has 8. 2, 4, 6. Now the oxygen has 8. But that's 18. I just did 18. So I got to stop because I've run out of electrons. Okay? And now you say, okay, well, we want to get octet rules, so what can we do? The sulfur only has 6, so it needs a pair. So I'm going to pick one of these oxygens. I'm just going to push a pair over. Okay? And that's going to become a second bond. Now, if we do that, we now have a double bond to the oxygen on the left. but we have a single bond to the oxygen on the right, and a single to the one below. This is called a double bond. Okay, so the sulfur has a different oxygen here, right? Like this is different here than it is to there. It's a different type of bond. There's actually two pairs of electrons holding those two atoms together. Okay, so a single bond, double bond. A double bond is generally shorter than a single bond because what happens is the more electrons that are holding them together, it tends to pull them a little closer. So this bond here would be a little bit shorter than this one would here. It also tends to be stronger. When you have more than one pair holding two atoms together, it usually takes more energy to break both of them than it takes to break one of them. So this bond here, this double bond, would be stronger than this one right here, or this one. Obviously, I haven't drawn them very well. Now, the point about resonance is this. This whole idea of Lewis structures works remarkably well, particularly for organic compounds. Like really drawing these very simple little structures, it allows you to really do all kinds of interesting analyses of molecules in chemistry. It actually gives us kind of a theory that allows us to predict reactions and things like that. However, it turns out that if you actually study the SO3 molecule in its detail, what you'll find is that all three of these bonds are identical in strength and length. It's not the case that one is shorter and stronger, and two of them are weaker and longer. Turns out they're all the same. So you start saying, okay, well, then there's something wrong with this Lewis structure. Because it's suggesting that we're going to have ones different from the other two. So here's what ends up being helpful to our analysis. It's called resonance. So see where it says include all resonance structures that satisfy the octet. Resonance, from a practical perspective, means what you do is you ask yourself, could I have taken a pair of electrons from a different surrounding atom? Instead of this oxygen on the left, would it work if I had used a pair from the other two oxygens? And so let's think about that. Is that possible? Suppose instead of doing this pair here, I would pick this pair over here, or this one here, or this one here, but this oxygen. Would that work? Would it mean that sulfur has A and all the other atoms have A as well? So let's see. If I take this pair, do that, okay, I'll do it to dash. Now what would happen? Now you have an extra pair between those two, and you have two lone pairs on this oxygen. So you have an extra bond there and two lone pairs. And then these would still be single bonds with three lone pairs. And you ask yourself, is that reasonable? Does that satisfy the octet rule for every atom? What do you think? Do you have the octet for every atom?
Yeah.
It does, right? It seems to work. So what we're going to claim then is if that's true, we can't ignore this as a possible structure. This is also a possible Lewis structure. The only thing that differs in this one compared to this one is the arrangement of electrons. If you get more than one Lewis structure, meaning more than one structure or two structures with different arrangements of electrons, and they both seem to obey the octet rule, we call that resonance. So there's two structures. So we would say, yes, there's definitely resonance as a possibility. But there's actually a third possibility too. Instead of this oxygen or this one here, we could have also used this one over here. We could have done this. Put the double bond over there. And that would work too. You get a third. So you have a double bond over here on the right. and then a single bond down here, and then a single bond over here. And again, each atom satisfies the octet rule. So it looks like we've got 3 possible structures that satisfy. And that's called resonance. Now, what happened was once people started looking into this, what they realized was in nature, what the atoms do with their electrons is they use their electrons as waves in a way to lower the energy of the molecule, to make it more stable, right? So like if I take this up here, it's less stable than it is here, because it has more gravitational potential energy. Here we're talking about electrical potential energy. So this molecule here has electrical potential energy, so do the other ones. What in nature,
Bye, everybody.
hey, take care, Mike. Thank you so much for everything, okay?
Good luck.
Thank you. What the electrons will do is they will actually take on an average of all 3. So what will happen is these electrons in this double bond will, some of the double bond will be here, some of it will be over here, and some of it will be down here. It'll take on an average of all 3.
So like 2/3 per bond.
Yes, exactly. That's what happens. And so resonance, even though it's really in a way it's a limitation in terms of Lewis structures, it actually gives us some insight into what's happening with these electrons. They're taking on multiple Lewis structures and then averaging those ones that we draw. So if you can draw more than one Lewis structure to obey the octet rule, then most likely what's going to happen is the actual structure will be an average of those. So now when we say, well, wait a minute, it turns out all 3 of these are identical bonds, meaning the same length and the same strength. Now we have an explanation for that. If you average these 3 values, you'll get 3 bonds that are identical. Right? It actually works out to be 1 1/3 bonds on average. Because if you take 2 here, 1 here, and 1 here, that's a total of 4 bonds over 3 atoms. The average would work out to 1 1/3 bonds on each atom. And that's called resonance. Okay? It's kind of an interesting phenomenon. Let's try another example.
Oh, wait, so for an answer, we're quick all 4 structures.
So it'd be 3. It'd be this one. This one doesn't satisfy the octet rule, right, for sulfur. So this structure right here is no good. But these other 3 are. Each of these satisfy the octet rule for every atom in the molecule.
So for in the center world, you always want to have a in the middle of the center.
That's where we're at right now. So right now we're enforcing this idea of the octet rule. Now we're going to revise that a little bit later, because it turns out nature is never simple. It does things in a more complex way. But our first sort of exploration of this is the idea that there seems to be a stability with 8 electrons around these atoms, except for hydrogen. Hydrogen is 2. The other elements seem to be 8. Okay. There's 1. Now let's just start this. Well, let's try this. CHO minus. Now, when you only have 2 atoms that are not hydrogen, there's not a lot of flexibility in terms of the arrangements. There's just, you don't have that many atoms to change electrons. And hydrogen is very limited. It's only going to just have a single bond to 1 atom. So, my initial thought on this is there may only be 1 structure and there is no resonance. But who knows? I could be wrong. So let's see. We have a carbon, so think of the carbon as the center, and then you've got a hydrogen. So just, put the hydrogen attached to the carbon, and then the oxygen. Okay. And now we count up electrons. So hydrogen is in group 1A. Carbon is in group 4A. And oxygen is in group 6A. And there's one of each, right? So that means we've got 1 plus 4 plus 6. But there's this negative. That's an extra electron, right? We got 1 extra electron. So we gotta add 1 more. So I'm gonna add 1 more here. So it looks like it's 12. Notice a lot of times you get even numbers. Even, that's a very common thing in nature, is that the number of valence electrons is even. Something about pairing electrons in these orbitals is giving them stability. Okay, so we got 12 electrons. It looks like we've already used 4. So minus 4, so that's 8. Not a lot of flexibility. We can't put any on the hydrogen, so they're all, those 8 electrons are going to have to go on these 2 atoms here, right? So just to be careful, the notation you use with ions is you put brackets and then you put the charge on the outside. That's just a notation. Okay. 8 electrons. So, like I said, I would put as many as it takes to get up to 8 on the surrounding atom first, and then work your way in. So there's 6, another 2 will be right there. Now that does give you 8 for oxygen, but it's only 6 for carbon. So we can't use that as a Lewis structure. That wouldn't be a valid Lewis structure because the carbon only has 6. You've got to get to the octet. So one way to do that would be to move a pair over, right? Just like that. So there's one possibility. And now we would have a double bond. Okay, so there's one possible structure, octet roll. Now, there is a problem with this Lewis structure, and that's why it looks like there is at least one more resonance form. There's at least one more. And the problem is the number of lone pairs on the carbon. Carbon is actually pretty unstable with a lone pair. Most of the time, it does not have any lone pairs. So let's see if we can think of another way to get an octet. What you could do is you could take this pair and push it over here between those 2 atoms. But what would that do? That would give the oxygen 10 electrons, right? So that doesn't look very good, right? That doesn't seem like an alternative. Because now that, if you took this pair and you made it a bonding pair, now the oxygen would have 10. So that doesn't look good. Is there any way, it doesn't look like there's much you can do, right? You can't just move this over. If you moved it over here, the oxygen would have 10 and then the carbon would only have 6. So it doesn't look like there's anything else you can do, really. Anybody have any ideas how you could move those electrons around and have 8 for each? I don't see anything. Like, could we move this pair over here and then move the bond out? 2 lone pairs on the carbon? That actually might work, right? Maybe we could do that. So here's a possibility. I'm going to get rid of this. Would be to move 1 lone pair over to the carbon, but then move a bond back over to the oxygen. Let's see if that works.
So break it, the double bond and make it a single bond?
Yeah.
But then that means two lone pairs are more stable than the second one.
Let's see.
And in doing that, I'm weakening the bond, right?
Well, yeah, there's a lot of implications of that, which is really fascinating issues, right? So the question now is, do we have the correct number of electrons? Do we still have 12? And we have an octet on carbon and oxygen. It looks like we do, right? 2, 4, 6, 8, 10, 12. No, we have 14. Right? Somehow in doing that, I added extra electrons. So that's no good, right? We have to limit to 12, right?
Because you added the two on the bottom of the.
Yeah, so I added an extra 2 to make 8, right? Because if I didn't do that, look what happens.
Six.
Now it's only got 6, so that's not an octet. So what I did was I made a mistake. I imagined moving the bond over here, realizing that that would give oxygen only 6. So I said, well, let's fix it by putting 2 more to give it 8. But by doing that, I added an extra pair of electrons that we don't have to give. So that is no good. That's not a real structure. That would actually, that would be CHO -3. And it'd be like you added 2 extra electrons. But that's not what we have. So that's actually not structured. So it looks like there's only one. It looks like our original one, where we have a lone pair here, and a double bond between the carbon and the oxygen. I'm just erasing that. That looks like the only possible structure that we have here. I can't think of anything else. I mean, I kind of thought maybe a triple bond here, but if you did a triple bond here, that would give the carbon too many. Look at how much you can do. So just one. So we would say, when it says be sure to include all resonance structures, that's a hint saying there could be more than one, but it looks like there's only one. Now, is that a good Lewis structure? My guess would be that this thing is probably pretty reactive. In fact, this thing is something that would actually be pretty reactive, because carbon is not, these 2 electrons are pretty reactive. Carbon is not, it's not real stable with a low pair on it, but that's not the question. It's just saying, can you draw a Lewis structure that fulfills the octet? It looks like that's one. Okay. Again, when you look at these structures, carbon is the one that's going to be the center, and then the other atoms are going to be attached to it. Just a little while. CO. This is called the carbonate ion, CO3 -2. This is a famous one because carbonate, well, actually worked with carbonate in the laboratory. When you did the molar volume of carbon dioxide, you took sodium carbonate and added I think sulfuric acid or hydrochloric acid. You added an acid to it, and then that produced carbon dioxide. So there's your carbonate ion right there, CO3 -2. So carbon in the center, 3 oxygen. This time I'll put an oxygen up here. Again, it doesn't really matter where you put the oxygens. Just sort of think of it as a box. We do know that it has a charge of -2, so just to get that out of the way, we'll put the little brackets there. And again, sometimes people just use a right bracket. They don't put the bracket over here. They just do half of the bracket. That's what let's do next. Let's do the accounting. Carbon is in group 4A. So that's 4 valence electrons. Oxygen is in group 6A. So that's 6 valence electrons, but there's 3 oxygens. So that's 18. And then you've got a -2. So that means you're going to add another 2 electrons. So that would be a total of 24. But we've already used 6. So that's 18. And then you can just do the same thing, put pairs on the surrounding atoms. I recommend doing the surrounding atoms first, till you run out of electrons. Okay, so that turns out to be 18, right? So 18. If we had 20 to work with, you would put the extra pair in the middle on the carbon. You don't want to go beyond 8 for any of the surrounding atoms. Okay? So we're almost there. We've almost got a valid Lewis structure. The only problem atom here is carbon. It's only got 6, right? A pair is 2, so 2, 4, 6. So we have 3 choices. There's 3 different oxygen atoms that could donate a pair to form a second bond. So how many resonance structures do you think we're going to have? 3, right? One of them will be where the double bond is here. Another one will be where the double bond is there. And another one will be where the double bond is there. So we have 3 possibilities.
So when we answer this on Alex, can we draw all three structures?
Yeah, it's gonna have you draw all three, exactly. And these can be kind of annoying on Alex, you'll have to really play with the, you know, where you put the, sometimes it looks like you put the lone pairs in the right place and then I think they've improved it a little bit better, so it's not as bad as it used to be, so. So it looks like we're gonna have three, so I'll try to draw all three here. So one would be where you have a double bond here. And then just single to the other two. And then when you do that, you're gonna have differing numbers of lone pairs, right? So there's one possibility. So just meaning the double bond is between this carbon and the oxygen. Another possibility is the double bond is between the oxygen and the middle. Somewhere here. So C double bond O. It doesn't matter which lone pair you choose. You just have to make sure you have the correct number. So again, this one, I'm showing the double bond being between the carbon and this oxygen. So this one, so that's 2. The third one would be this one over here. C double bond. Sometimes people will simplify it and just show the bonds and not the lone pairs. But be sure to put the lone pairs because when you're learning this, they want to make sure that you know how to draw lone pairs. And then it's going to be an average of all three. So there is not going to be an actual double bond anywhere or a single bond anywhere. It's going to be an average of a double, a single, and a double. I'm sorry, a double, a single, and a single. So that's 4/3 of the bond, right? 2, 3, 4 bonds over 3 atoms. On average, that's a 1 1/3 or 4/3 of the bond. So a little bit stronger than a single bond. You can study this stuff. You can make molecules. You can study molecules and see like, hey, how strong is that bond? And then say, hey, how strong is that bond? You can make that molecule and see how strong that is. And then you study this one, and what you find is it's in between those two. It's stronger than that, it's weaker than that, which means it must be an average of both somewhere. Okay, that's called resonance. So that one has 3 resonance forms. In general, if it's one of these molecules where you have surrounding oxygens, the number of resonance structures tends to be equal to the number of surrounding oxygens. So if I had, for example, PO4, you'd have 4 surrounding oxygens. Most likely you'd have 4 resonance structures. A double bond to one, a double bond to the other, a double bond to the third, a double bond to the fourth. That's often how it works. I do want to show you, just real quickly, that we can test the discussion from the earlier section about formal charge. Because formal charge is kind of a new idea, and I just covered it yesterday. So remember, formal charge is a calculation you do for every atom in the Lewis structure. Unless it's a test problem where they say just do for this one. Okay? The formal charge is a calculation you do for the atom to test whether that particular Lewis structure gives good results. It's like a separate test than the octet. So we have the octet, that's good. The formal charge is done, what you do for each atom is you take the number of valence electrons. Again, you've already done that when you did the Lewis structure. You're just looking in the periodic table. Carbon has 4 valence electrons, oxygen has 6. You subtract off the electrons in the lone pairs. So you subtract off the lone pair electrons. And a lone pair has 2. So for every lone pair, you subtract 2. And then you subtract the number of bonds to the atom. And in general, there's a couple of rules of formal charges. One is, if you get a negative value when you do this calculation, the negative should be on the more electronegative element. Oxygen is one of the most electronegative elements, 3.5. So if you get a negative formal charge, it should be on the oxygen. Carbon only has an electronegativity of 2.5. So the best Lewis structures are not going to have a negative for the carbon and a positive for oxygen. You're more likely to get a negative, a positive for carbon or a 0 for carbon, and then a negative on the oxygen. Okay. So let's take a look. I'm going to do this oxygen here first. I'm going to put just a little A here, just so we know which oxygen we're doing. So I'm going to do the formal charge for oxygen A. So oxygen is in group 6A, so it has 6 valence electrons. Oh, I shouldn't do this one up here, right? I should do one of these, one of the final structures. So let me do this. Put A over here. I'm just going to do this one right here. Okay. So here's oxygen. So oxygen has 6 valence electrons. Subtract off the lone pairs. You get 2 electrons for every lone pair. So there's 2 lone pairs, so that would be 4, 2, 4. And then you subtract off the number of bonds. This oxygen has 2 bonds. You get 0. In general, the closer you get to 0, the better. So if you have a Lewis structure and you get 0s, that's usually a sign it's a good Lewis structure. So I'm going to write the 0 here. That looks pretty good. 0. That would support this Lewis structure. It's not proof that it's the good Lewis structure, but it's evidence. Now let's do this oxygen over here. I'll call this B. So the formal charge for oxygen B, same idea. Number of valence electrons, it's oxygen, so it's 6, that doesn't change. But now you have 3 lone pairs and 1 bond. So see how those 2 numbers change? The number of lone pairs is now 3. Each lone pair is 2, so that's 6. And the number of bonds is 1 instead of 2. So now you get -1. So this oxygen has a formal charge of -1. And what we do is we think of formal charge kind of like a charge. Even though it's a covalent molecule, it's not ionic. We think of it kind of like a charge. It's sort of like the oxygen here is neutral. This oxygen here has a charge of -1. Okay. If you look at this oxygen up here, same thing. We'll call that C. 6 valence electrons, 3 lone pairs, so that's 6. 1 bond, so that's 1, and you get -1. So this one ends up being the same, -1. Okay. And now let's do the carbon. I'll call this D. So the formal charge of D. Now this is carbon. Carbon is in group 4A, so the valence electrons is 4. It doesn't have any lone pairs, but it has a total of 4 bonds. So you get 0. Now, looking at this looking at these formal charges, notice a pattern. If you add them up, they add up to -2. That's actually the same as the charge over here. And in general, when you do formal charge calculations, adding them all up will give you the charge of the ion itself. If it was a neutral molecule, they should add it to 0. The other thing is, if there are negative values, the negative values should be on the most electronegative elements. And in fact, they are, right? Oxygen is the most electronegative element in this substance. It has a negative formal charge in 2 of the atoms. Carbon is less electronegative. It has a formal charge of 0, not -1. So this information here, to some extent, supports these Lewis structures that we've drawn. Okay, they at least don't say that they're bad. What would mean it? You know, how would we interpret it if this came out to say -1, +1, -1, +2? The further away from 0 you get, that lends support that it's not a good Lewis structure. So for example, over here, we know this is not a good Lewis structure because it's not the octet. But if you take a look at it, for the carbon, 4 - 3, because there's no lone pairs, this would have a formal charge of +1. 6 - 6 - 1, this would be -1. All of these would be -1. So if you compare these numbers here, these formal charges, which I just sort of did in my head right there, those formal charges are further away from 0 than this set of formal charges are. 2 of them are 0 here, none of them are 0 here. So even though we can reject this because of the octet rule, we could probably also reject it because of formal charge calculations. Okay. Closer to 0, the better. If there's any that are not 0, the negative should be on more electric. Okay. Now that's mainly discussed in the previous section, but I want to go over that again just to show you. Okay. Let me do one more. Ozone. Ozone's a fun one. It's not charged, it's just O3. It's a interesting form of oxygen. So when you have one oxygen, this is often referred to as atomic oxygen, because it's an atom. When you have O2, this is referred to as molecular oxygen. It's a molecule. And then O3 is referred to as ozone. People have studied the idea of O4. Right? So there's some calculations and measurements people have done about before. So ozone, it turns out, just draw 3 oxygens in a row. Just like that. And then if you do your valence electron calculations, there's 3 oxygens, each one's in group 6A, so that's 6, so that's 18. Subtract 4, that gives you 14. And now here's an example where you can get the surrounding atoms up to 8. So there's 6, 8, 10, 12. We still have 2 to go. So now we put them on the central atom. That's 14 right there, right? Let's check. We should have a total of 18. 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. Okay. Now we're almost there. This oxygen has 8, this one has 8, but this one only has 6. So we could take a pair here. That's one possibility. And that would be, both of those would get counted, so that would be 8. And we would have a double bond over here. And just a single over here. That's one possibility. But there's another surrounding oxygen, right? So what if we done this? What if we taken this one and done it that way? It's another possibility. So instead of doing it over here, we'll do it over here. So now you have a double bond over here. Don't forget the lone pair here, it's already there. So it looks like there's 2 structures, right? 2 possible resonance structures. And it's going to be an average of the 2, right? So the average of 2 bonds and 1 bond is 1.5. So in fact, the ozone molecule has 2 bonds that are really 1.5 in terms of their strength and their length, but we have 2 resonance bonds. Okay. That's resonance. The nice thing about that section is that you're really doing a lot of the earlier stuff you're doing, like electronegativity is a little bit of the discussion, the octet rule, the arrangement of atoms, and all of that. It's all in that type of problem. All right, so it looks like the next topic is exceptions to the octet rule. So we'll cover that tomorrow. But I want to give you a little heads up on it. So, we really drill home this idea of the octet rule, but it turns out things are a little more complicated than that. It turns out that there seem to be molecules and ions where you can draw Lewis structures that are not octet. So for example, this one right here, the chlorine has 2, 4, 6, 8, 10, and you say, hey, you're violating the octet rule, so that's no good. But it turns out the evidence suggests that this might be better than the actual octet. And so sometimes it appears as though some atoms will have more than 8 electrons, or even less. Sometimes they can have less. So we'll talk about that tomorrow, and then we'll talk a little bit more about this idea of bond energies and bond strength, which is called bond energy. So this is sort of bringing it back to energy. We'll come back to this idea of delta H, but looking at it from the perspective of chemical bonds. And that will give us some insight into chemistry in that we can talk about energy changes based on the strengths of these bonds. And then we'll be at the end of chapter 8. Okay, so enjoy.
When is our last Zoom meeting? Is it next week or we finish on Thursday?